All right. So that should help. I hope that helps a bit to kind of sort this out. You need to pay close attention to what the name of the ester is and how to dissect it so you get the right portions. So go back into here and look at some of these. You know, here's ethyl butanoate. So look at some of these and see how do we get these names. Here is propyl ethanoate. Propyl ethanoate. Yeah, and whether it is the sodium salt of the carboxylic acid or the ester of that carboxylic acid, we keep that portion of the name the same. That is the ethanoate. Ethanoate. When it's got a hydrogen on there, it's ethanoic acid. All right, these are the reactions that we went through. Acid hydrolysis, saponification. Saponification of a triglyceride, making soap. Did I talk about this, how the soap molecules function as soap molecules? Okay. Yeah, they emulsify. And they're doing that because they have a dual character. They have a water-loving end and an end that doesn't like water, isn't compatible with water. And it's all stuck on the same molecule. So there's a polar head and a non-polar tail, and that's what gives it its surfactant properties. Okay, now, phosphate esters. What is a phosphate ester? To make an ester, to make just a regular ester, we took an alcohol and reacted it with a carboxylic acid. To make a phosphate ester, we're going to take an alcohol and react it with phosphoric acid. Now remember, your regular ester functionality looks like this. You got this carbon, oxygen, carbon with an oxygen double bond to it. There's your ester. Well, what do we have here? We've got a carbon, oxygen, phosphorus with a double bond to an oxygen. So hence the name phosphate ester. These are extremely important in biochemistry. This phosphate group shows up on so many different molecules in the metabolic pathway and critical at very critical points. You've heard of ATP, adenosine triphosphate. It is a phosphate ester. So ATP is a phosphate ester. ADP is a phosphate ester. And the conversion from ATP to ADP releases a lot of energy. Your body is constantly, while you're sitting there right now, you're producing millions of ATP molecules. Your body's continually resupplying its ATP and making it available then for use, for energy. That's where you're getting your energy. So metabolically, we're producing this, and it's phosphate ester. This is ATP. So that's adenosine. It's attached to a sugar, ribose, and then it has this triphosphate. And here's your phosphate ester right here. So there's a phosphate ester linkage to the sugar, and then that is linked to another phosphate, which is linked to another phosphate. All they're showing you right here is that all these hydrogens in the original one where you had OHs here, at the physiological pH, those hydrogens are hydrolyzing off, and it is charged. It's got a negative charge to it. And there's your ATP again. adenosine, the ribose, the triphosphate. You break that bond right there, and ATP becomes ADP. So ATP is going to ADP. And it's cleaving off a phosphate. Here's your phosphate coming off, plus a lot of energy, 32 kilojoules per mole of ATP. So one mole of ATP breaking down into ADP can release 32 kilojoules of energy, which is a fair amount of energy. That's a pretty high energy bond there, that phosphorus-oxygen bond, compared to like a carbon-carbon bond, some other bonds. That's a pretty high energy bond. So the body's chosen a pretty good molecule to pack some energy into it. Yeah, and every cell of your body has some mitochondria. In those mitochondria, it's producing ATP. It's not like your bloodstream is supplying that ATP to your cells. Your cells are producing it. Each cell of the body is producing the ATP. So a couple trillion cells in your body, and they're each needing a number of ATP molecules kind of on a continuous basis. You're constantly converting stuff into ATP, and it's breaking down into ADP and releasing the energy. So it's keeping you going. This little process right there is what keeps you going. It's really kind of amazing biochemistry. Eat a little bit of sugar, it goes into the tricarboxylic acid cycle, the TCA cycle. It produces electrons that go in the electron transport chain, and those electrons then reduce oxygen and produce ATP. It's incredible. All right, there's 3 slides there, those 2, this one, and finally this one, that are doing all the same thing, summarizing the reactions of chapter 14. Summary of reactions. What happened? Oh. Man, the more I touch this, the more it makes it worse. Okay. So I don't need that anymore. All right, so this is a pretty good summary. And if you go on into any exam, you should go back and look at these reaction summaries. And also, I really think probably after spring break, the Wednesday after spring break, we will, it says there review for the exam, but the other thing we will do that day is have a reaction quiz. It'd be a short quiz, 10 or 20 point quiz on reactions of probably chapters 12, 13, and 14. It will cover the reactions of those chapters.
You said the Wednesday after spring break?
Yeah, I think it's like March 21st. All right. I'll hand out the chapter 15 homework today, but it won't be due until after spring break. Okay, let's just look real quickly at the summary. How would you prepare carboxylic acid? So this is just a review of what we covered. You take a primary alcohol, you can oxidize it to a carboxylic acid. You can take an aldehyde and oxidize it to a carboxylic acid. So those are ways of preparing carboxylic acids. How do they behave? Well, they dissociate. You put them into water, and they don't dissociate 100%, but enough to make the water acidic. They are weak acids. So they're weak acids. They partially dissociate, forming an anion and a hydrogen cation. That's your acidic proton coming off of your carboxylic acid. Okay, now reactions. Since it is an acid, it will react with a base. So you can take that acid, react with a base, form this salt and water. This is really the only time where it's really appropriate to kind of be showing the negative positive charge. This is an ionic compound. That's appropriate. But I mean, esters are not ionic compounds. This isn't an O minus R plus group right here. This is a covalent molecular compound. It doesn't just dissociate in water. So here is your real classic esterification reaction. Carboxylic acid plus an alcohol forms an ester and water. It's a dehydration reaction. You're getting that water right off of the acid and the alcohol. Okay, then how do esters react? You take an ester, you can react it with water in the presence of acid, and you'll get back the carboxylic acid and the alcohol, just what we did over there. That was the acid hydrolysis of 2 esters. Saponification. Yeah, I got to change 2 slides in here. This should be in here as a reactant. I don't know why I'm so particular about this, but I just, if you had a mole of ester, you'd need a mole of sodium hydroxide to react with it. So it's not a catalyst, it's actually a reactant. There's a lot of similarities between this and that. I mean, here you're reacting with water, you're getting an alcohol and a carboxylic acid. If we react with NaOH, what do we get? We get plus an alcohol. Right, so there's a lot of similarities. If we took that molecule and reacted it with this, we would get the sodium salt. We would get the sodium salt of that and the alcohol that came off of there. R2. All right, so a lot of similarities. Here we're reacting NaOH. Here we're reacting HOH. I don't know. When I think about it that way and see how similar it is, it helps me anyway. Okay? There's not a huge amount of difference. They got big different names in them. This one is more soluble in water. We get this sodium salt. It is really an ionic compound, and it is more soluble in water than the carboxylic acid is itself. In the lab, you can take, to kind of show you that, you could take, here is a carboxylic acid that is not soluble in water. Benzoic acid. This is not soluble in water. But if you take that and react it with sodium hydroxide, what you get is this and water, and this is soluble in water, not soluble in water. So there are some basic things that you can observe and basic differences between the sodium salt and the carboxylic acid to begin with. Okay, back to our reactions. So we got all the way down through here. We went over to saponification. These two reactions, you be aware of them to the extent that you see them right there. You could take a carboxylic acid reacted with a like HCl and form an acid chloride. See, we're replacing that OH with a Cl. You don't need to be responsible for these two reactions. Just when you make aspirin in the 1107 lab, if you are going to do that, if you're in the 1107 lab, you're going to take salicylic acid and react it with acetic anhydride to form acetyl salicylic acid. So that's one time when you'll come across an anhydride. That's an anhydride. You got a carbonyl, an oxygen, another carbonyl. That's the anhydride functionality right there. And then phosphate ester, don't worry about writing out reaction this and that and the other thing to produce a particular phosphate ester, but do be able to recognize what a phosphate ester, what that generally looks like. Instead of a carbon there, and that's all, just a carbon, we've got a phosphorus, and it actually has 4 oxygens around it. One of them is a double bonded oxygen. Phosphorus can actually get 5 different things around it. Yeah, there are 5 bonds. It has 2, 3, 4, 5 bonds around it right there. So that's your phosphate ester. Okay, are there any questions about chapter 14? Anything you'd like cleared up or like me to go over again?